Let's see, don't mess up. Okay, so A124 office hours. There were only a few people for the first hour. We answered a bunch of questions already. I just erased one of them, but a bunch more people showed up, so I decided to go live and make a video of the questions. And we just got a question that I really don't want to answer because the question is,
how big are superconductor band gaps compared to regular conductor band gaps?
so the idea of band gaps, right? We can draw these different things. That would be my representation of an insulator. That would be my representation of a that would be my representation of a semiconductor. This would be my representation of a conductor. And then superconductor kind of breaks this picture, right? So technically I should still, someplace in my conductor, I should still have like someplace there's like this area where there's like the valence band and the conduction band are crossing each other. And what would happen in a superconductor, going for this cartoonish picture, and this is a complete oversimplification, does not capture the interesting aspects of a superconductor at all, you would essentially say you've got like complete overlap of your conduction band and your valence band. Super oversimplification. Superconductors are, in my opinion, one of the most fascinating materials that exist right now. There's a lot of really, like, I actually, on my newsfeed, I get updates about superconductors, and there's like in the last 10 years, the research and things happening with superconductors has been like really fascinating. There's like there's materials that are just exhibiting surface superconductivity. There's a new model for how superconductivity works that instead of, so normally what happens with superconductivity, the prevailing theory has to do with like electron pair traveling. So essentially, like, you know, you got your electron spin up, spin down. In superconductors, the electrons are actually able to pair, and that's what allows them to move through the materials because they stop interacting with the like nuclei and they start interacting with each other. There's been a new material that they just, there's a new theory for a particular material that has unexpected superconducting properties where they actually think it's 3 electrons interacting with each other to create a triplet that's creating the super. It's the first time they've ever seen that. So this
is this technically smaller than a normal conductor, or
well, so they're both no gap, right? But like, you know, someone made the joke before I started recording of like it's negative gap, right?
Yeah.
And you can almost start thinking about that when you're talking about conductors, right? So you can imagine this situation, right, where you've got like a really tiny gap, and you can imagine the situation where actually your gap is almost as big as the bands, like the spaces between the bands, but your gap would be right at the middle, and this would be like a 0 gap. And then when you go to conductor, you start crossing these.
Sure.
And then the question becomes, how much do they cross, right? With this cartoon kind of simple hand-wavy representation of conductivity, the more they cross, the better the conductor would be. 100% crossing would be a superconductor, right? The electrons are able, but really does not get the complexity of superconductors or even conductors, really. But it's a good, like, energetic first step. And which problem was that?
3.
3. That was problem 3, which was asking about the band gaps for the different materials. There was a question somebody asked earlier that I also wanted to address, which is this idea. I'm going to make my band gap a little bit larger again. I'm going to get rid of that. So there was somebody asking about the lab that was asking about why change in temperature affects conductors differently than it affects semiconductors. And that was an important part of the lab for our understanding. And the idea here is, in conductors, because you have this overlap, because you have complete overlap, there doesn't need to be any additional energy to get electrons into the conduction band, right? They're already in the conduction band, right? In a semiconductor, we've got our electrons in the valence band, and we don't have electrons in our conduction band. And these are like physics terms. I would call these the highest occupied orbitals and the lowest unoccupied orbitals, and our transitions will be between those two, right? So the thing that happens here is I need some energy to get into the conduction band. That energy can come from any place where I put energy in. So if I put in light stimulation, light's energy, right? Photons of energy. If I attach a battery and do electrical stimulation, that's electrical energy. If I heat it up, thermal energy. The thermal energy will help the electrons get across the gap. Since there's no gap here, the thermal energy is, so in semiconductors, it's a very energetic argument. In conductors, it turns out that you have a hand-wavy physical argument. And this is because whenever we're building up and we start doing average effects, we start to lose some of that kind of energetic quantum mechanical atomic molecular scale understanding. And the kind of clownish argument that people make is, oh, when you cool it down, the atoms vibrate less, and it essentially makes a hallway for the electrons to like run down.
But in a conductor.
In a conductor, right? So when you cool it off, you make space for the and it's just like the electrons are not like running down a hallway, right? Like conduction does not depend on one electron traveling the entire line. Conduction is more like this, where like the electrons bump each other across. So conductivity, I put one electron in, I pop one electron out the other side, but I can't catch what I'm holding. So this idea of like you create a hallway for electrons to run down is kind of silly, but works in a kind of hand-wavy explanation way. Cool. Question, yeah.
How does that affect like intensity though?
So intensity, it turns out, so when we cool it off, we also start to get higher intensity, right? So that has to do with which energy transitions we're dealing with. So when we get rid of our thermal energy, so essentially the thermal energy randomizes the energy a little bit, right? Because thermal energy is just this extra energy that bumps things around. And essentially when we think about like which energy levels are populated, we can be populating like all of these levels, right? And as we cool it down, we start to kind of move electrons out of some of those top levels, and we start to move them down. Again, taking out that thermal energy is going to cause that type of cause that change in energy. Now, instead of exciting to a whole series of things, because the main thing we have to realize when we're doing band gap theory is we are going from a group of levels to another group of levels. And so what I'm going to see, rather than seeing a sharp line, from going from a group of levels to another group of levels, I'm going to essentially see this kind of curve where I've got the most probable. That's my most likely transition, but I'm going to have a couple that go from the top to the bottom, right? I'm going to have those little transitions, and I'm also going to have some that go from higher up to further down. That's going to be those higher energy transitions. When we cool this, we essentially crunch this down. We still have the same number of transitions, but now we crunch it down so that they're all kind of occurring in a tighter area. And that's going to give this appearance of an increase of intensity. So instead of making a bunch of wavelengths, we start making fewer wavelengths. That's going to give that appearance of the increase in intensity. And then we're also going to make this gap larger, which is going to give us the shift in wavelength. So again, just like the difference between insulators and conductors for how temperature affects them, the change in wavelength and the change in intensity are two different ideas. And again, a little bit hand-wavy. This is a a good kind of cartoon representation of what's going on.
And then for a superconductor, how does temperature affect a superconductor? Is it health or?
Ooh, so how does temperature affect a superconductor? Turns out these materials, and this is again why this picture totally doesn't work, right? Because what happens with a superconductor, if we've got our bands, most superconductors don't conduct, don't conduct, don't conduct. You hit a particular temperature called the critical temperature, superconduct. So rather than doing this like slowly approaching people, like slowly approaching or like spreading, this material, you hit the right temperature and all of a sudden it just becomes a superconductor. And that's where you can really see that this model does not capture the behavior of superconductors.
So it just totally depends on what superconductor you're talking about?
Yeah.
Okay.
I mean, they all have this cartoonish idea of the bands exactly overlap, but the temperature at which superconductivity starts to happen is completely different depending on the material. Most superconductors, 4 Kelvin. Liquid helium-cooled superconductors.
Wow. Okay.
Whenever they talk about high-temperature superconductors, a high-temperature superconductor is 77 Kelvin. Now keep in mind, that's still minus 200 Celsius. But in terms of superconductors, minus 200 Celsius is high temperature. Temperature is relative. My brother thinks 50 degrees is hot these days because he's been living in Alaska. Like 50 degrees is not hot. Sorry, back to chemistry. Questions?
Okay, on number 8, it's...
Well, hold on. We had some hands behind you. What's your question?
For number 10, what does it mean by like which group does X belong to?
Ah, yeah. So this is the problem where you had different materials, and I left something mysterious. Do you want to pick one of those materials?
Can you pick? Is C okay? Because I didn't understand C.
MCO3. I know which one is C.
Yeah.
Because everyone was like, oh, I can't do this. So the question becomes, oh, was it XCO3?
Yeah.
So M is what we use for generic, like metal. X is usually just generic thing, right? So we want to figure out what group X belongs to. Now the problem with this is we know the oxygens typically have -2 charges, and we've got 3 of those, so that's going to be a -6. Right, so that's going to be a -6. The carbons have a huge variety in their charge. I just happen to know this one's going to be +4. So we've got a +4. So overall, this thing is going to be -2. Now, how did I know that? Because I did a bunch of chemistry. Or, what you can really notice is remember how I've been saying you should start looking at that list of common polyatomic ions? We need to start learning all of them. Carbonate is one of our common polyatomic ions. Carbonate anion is the CO3 2-. After you know that, it becomes really easy to say what X is related to. Looking at the periodic table, notice I want this thing to be overall 0 charge. So I need a metal, and I've only got one of them. I need a single metal that's going to balance a -2 charge. Alkali earth metal. X has to be in the alkali earth metal group. Come in. There's 2 chairs in here. Come. Alkali earth metal. So if we look at the periodic table, what is that going to be? Beryllium. What's below beryllium?
Magnesium. Mg.
Magnesium. Calcium.
Oh, wow.
Cadmium CD.
Oh, okay.
Calcium and below calcium.
Well, SR, I'm going to guess that's...
Strontium.
Okay, well, that's not a fun guess. Yeah, and then Ba.
Barium.
And then Ra. Radium?
Yeah.
Yeah, dude. Call me Einstein.
So, it turns out beryllium, probably not going to be that one, just doesn't have that much. But magnesium, calcium, strontium, and barium. Also, radium, radio is not stable, it's radioactive. Not that one. Beryllium, it could be, I just haven't, it's just like, it's again, remember, we have to start thinking about not just what we can do, but what's practical. I've just never seen beryllium carbonate. And now I kind of want to look it up and see if that's a real thing or not. Because I don't think it is a real thing, but I don't know why it wouldn't be a real thing.
So do we have to actually
Jason?
like know which element?
No,
If
no,
we
you
are
just have to say alkali earth metals.
Okay.
Or you could just group 2 would also be fine. Question?
Need to know the polyatomic ions for this quiz.
Not for this quiz,
But there is the quiz.
but we'll do a reading quiz next. We'll do it, not a reading quiz. We'll do a nomenclature quiz next week. So we'll know the polyatomic ions by next week, next Friday. Remind me to say that in class. Yeah. Question about this one or something else? Okay, I'm gonna move on. We good on this one?
Yeah, I moved it because it's
Oh wow. Okay. Now I want to know all about it, though, so I'll look that up and just read about it later. It just doesn't seem that common. Other questions?
Okay, sorry, I can you read what 90 is?
Use the condensed electron configuration moves the oscillators to the ions formed from each of the following atoms and predict the formula of the compound. So you want C, right?
Mhm.
And C is Al and F, so aluminum is fluoride.
So, what's the likely? So if I look at fluorine, how many electrons does it have in its valence? How many electrons does it want?
8.
Right, so that means one
okay,
more.
okay, yeah.
So it wants to be, that would be fluorine.
Mhm.
I really don't like dot diagrams for this, but it's okay. When I look at aluminum, where's aluminum on the periodic table?
Group 13.
Group 13.
Plus 3. 3 or
Right.
2.
Well, I want to see the periodic table so I can get the right number of dots. So aluminum, not technically transition metal. No, it's just outside. And it's got 3 valence electrons. Go to Al3+. Turns out aluminum almost always, well, aluminum pretty much always goes to 3+. So when I put these together, AlF3. Right, and again, in these cartoon, electrons are dots in one spot. They're not dynamic, like silly. But we can imagine fluorine, due to the electronegativity difference between these two, could steal an electron from aluminum, and then another fluorine could do that, and then another fluorine could do that. And that's where we get AlF3. You'll notice that actually, and this type of picture argument is really important to understand if you're learning about chemistry just from periodic trends in the periodic table. And not even the trends, but just a lot of times in high school, a lot of times in chemistry classes at community colleges and other places, you learn chemistry by electron counting. You say periodic table tells us how many electrons, electrons tell us how many things bond. Since we've learned a little bit better, I'm gonna go with better, because I actually do like this way better, right? So we learned the periodic trends. We learned electron affinity, ionization energy. We learned the quantum energy ideas around this. We can actually make a energetic interaction type argument for why aluminum is +3 and fluorine is -1. We can look at this and say, due to the electronegativity, that is to say the ionization energy and electron affinity associated with fluorine, it is likely to pick up an electron. Due to the, and then you can also bring in like the full shell quantum mechanical energy arguments for why it stops at 8. And you can do the same thing for aluminum and say, why does aluminum lose electrons instead of gaining electrons, right? And you can make those same type of arguments. So with that in mind, I find the dot pictures more cumbersome than helpful because of the way we do it. We don't need to use the periodic table as a magic thing that tells us the number of valence electrons. We can just think about the trends and the energetics involved. But the question asks us to do dot diagrams. It's warming us up to do Lewis structures. So, you had a question on 8?
Yeah. So the first one, A, is I got.
What is question 8?
8 says state the type of bonding you would expect in each. A is cesium fluoride.
Well, I had a question. It has like an S or a G in parentheses after the elements that you named.
Right, so cesium fluoride is solid.
Oh.
Then it's got N2, which is a gas. Then it's got Na,
okay.
which is solid. I almost put gas. It's not a gas. It's a solid.
Okay.
So, what type of bonding in cesium fluoride?
Which are usually solid.
N2. Na.
Metallic.
Oh, well, yeah, but.
Yeah, it turns out that sodium is an alkali metal, and it actually exhibits metallic properties. If you could get solid sodium, we have some in the stock room. And I could pull out a little sample and I could show you it's actually shiny like a metal. It actually bends like a metal. You can shape it like a metal, and it's actually a very soft metal, so it's very easy to shape. It's almost like a putty. You can't really demonstrate the fact that it conducts electricity or heat without it reacting with things in the environment. You can only do that in a situation where you've got it completely closed off. If you apply heat or electricity to this, it'll react with the oxygen in the air and start to burn. So to exhibit those behaviors, you have to isolate it in like a non-reactive environment. But it has all of those metallic properties. That's part of why it's, and everything in that column, in the alkali metals, will exhibit metallic properties if you can get them in their metallic states. They're just very unstable in their metallic states because of their ionization energies and their electron affinities relative to everything around them in the world we're in. Other questions? Yeah.
So it's at the end of the homework. I'm not sure what letter it was,
Okay.
but it was drawing the Lewis structures for where this one was C3H7NO3, and then it asked to add a carboxylic acid and NH2, and I wasn't sure whether include that on top of what you're given or just make sure that that's included.
Just make sure that's included.
Oh, so not like to nitrogen.
Let's see. What am I missing here?
Just 2 hydrogens on the
Hydrogens and C's.
Yeah. Yep.
And then one more.
Yep.
Ta-da!
Stuff on. Oh.
That's it. Now, I drew this in a very particular way because I wanted to draw it with a carboxylic acid. And another functional group we should learn, when we have this type of nitrogen, we call it an amine group. And so this is amine with an acid. Not aminic acid. This is a category of compounds where we can replace. Oh, did I draw this wrong?
You need a long tail for that.
I am missing something. Okay. I knew I was missing something. I'm also missing something else for what I actually wanted it to be. So let's change this just a little bit so it can be what I actually want it to be. I think that's right. Oh man, I can't post this video now because my colleagues are going to make fun of me. So it turns out that this situation where you've got an amine and a carboxylic acid, and you've got this carbon in the middle, where you can kind of change what this functional group is to a lot of different things. This has a special category of names for it. There's a special group of compounds called amino acids. I hope I drew it right. Don't make fun of me. I do P-Chem. Talk to me about quantum mechanics. They're not going to talk to me about quantum mechanics. But so this is one valid structure, right? And this is kind of the structure I was hoping for. But there's a lot of different isomers that would also be valid, right? you could put the NH there and this thing there. You could move the OH down here. There's a lot of different things you could do, but this is where you get to like this idea of like an amino acid.
On the quiz, will formal charge be on the quiz?
No.
Are we doing that?
So 18 and 21 are not on the quiz.
Okay.
Sorry, I forgot to send an email out about that.
Oh, so that's
16, I think, is
It's about
valid.
polarity.
Oh, what's 16?
Yeah, arrange the bonds and
Increasing.
Increasing.
16, 18, and 21 will be on the quiz.
on 20. It asks for a circled group.
Circle the functional groups.
It said like label the circled group, but there was no circle on the group. Was
Did it not also ask you to circle functional groups?
For the following molecules, name
the
the
circle?
circled functional group, but none of them are particularly circled, so I assume you just find them.
Oh, just circle. It should say circle the functional groups and name them.
Okay. All right.
Yeah.
Question on 17. It was N2O2, and I was wondering, cause the way I did it was I paired two N's together and then double bonded into two O's. So each N had an O basically.
Mm-hmm.
But then I looked it up online and it didn't look right. Like it wasn't the same thing that I had.
So, you did it like this?
I did it like that, and I put the dots obviously. And I was wondering if that's right.
How did it have it online?
Online it had like the O like alternating. It was weird. I don't know what it looked like. I forgot what it was. It did look like that. I'll look it up right now. But was that right?
So, I think what they're going to have online is the other various resonance structures for this compound, right?
Okay.
So, in terms of, well, is this right? This is a valid Lewis structure. So this is one of the possible Lewis structures. Were the other ones still O-N-N-O? The ones that you saw
Yeah,
online?
yeah.
So if we do some switch where we do like O-N-N-O, that makes me unhappy. What did they do for theirs? I need something else to make me happy.
I kind of forgot. It didn't look like what I had. It
So-
could have been a resonance structure. Or
So
something
there
like
are
that.
various resonance structures, and we haven't talked about resonance structures yet, but this idea of there are other least energy configurations that we can do.
Oh, it was charged. That's what it was.
Oh yeah. So it would have like a single bond here plus here with another
Yes.
there, blah, blah, something like that.
Exactly. Yeah.
Yeah. So there are some, and I'm like keep erasing things. I'm like, would it have that? Or would it have it there? Would this be minus? That would be plus. And then I think you'd actually not have those two there. But I want to go through and actually do the counting of electrons to make sure, because now I'm curious. But there would be various resonance structures.
Okay.
But the Lewis structure you drew is a valid Lewis structure.
Okay.
But you got to keep in mind, like what we're representing here is not going to completely depict reality because there's dynamics here. The electrons are not stuck in one spot, right? Realistically, we should draw like a probability distribution cloud. I don't know why I drew that O so big. We should draw some probability distribution cloud of like where the electrons are more likely to be and where the electrons are less likely to be, and we should have this whole like probability distribution of the electrons over the entire thing.
Okay. Got it.
But it's hard to draw pictures of that on
Yeah.
like a piece of paper to represent reactions. So we go with like an average kind of close enough phenomena, which is what Lewis structures are. Right, and this gets into one of the great, but for me when I was taking chemistry, really frustrating things about chemistry. This, in terms of understanding what's going on, is like 80% of the answer with like 30% of the work.
Right.
To get the rest of the answer is a lot more work. And so when I took chemistry, I always got really frustrated because I knew that it was more complicated than like I was being told. And I was like, why don't I understand, like, I feel like it should be more complicated. It's like, yeah, it's a lot more complicated. You know, we can do 70% more work and get, like, we can do like 60% more work and get like 10% more accurate. Or we can do a fraction of the work and be close enough.
Okay.
So it really gets to, did anyone watch that video of Feynman I sent out?
I've seen it before.
Okay. So it gets down to this idea of like, how deep does the answer need to be for your question to be satisfied?
Right.
Right? And this is close enough for a lot of what we're going to do, but there's deeper questions we could get to. There's a lot more we could get into about the dynamic nature of bonds, the dynamic nature of electrons, the energetics, the vibrations, the rotations. There's a lot more we could get into.
Okay, right on.
But like close enough.
Could you, for this Lewis structure specifically, if you wanted to erase the lone pairs on the nitrogens and just make that a double bond?
So yeah, could we do this?
Like, I'm just like trying to understand how to create Lewis structures correctly. Like, as long as there are 8 electrons around it, like, it's fine, right? Like, is that fine?
However, remember we also have to, so if we're doing our formulae, and this is where people who are really comfortable with Lewis structures, they're like, oh yeah, I did in high school, it's no problem. It's like, you get to these weird compounds, you get to something like SO4 2-, and suddenly you're like, oh, we didn't do anything like that. And this is where getting to our kind of like systematic way of like count electrons, make a skeleton, fill valence. Check like this systematic method that I talked about in class that like we did for water and carbon dioxide, and you're all like, why are we doing this? For N2O2 in these situations, this is going to let us see that this structure is actually not valid. You've got your octet satisfied, but I don't think you have the right number of electrons. So nitrogen brings 5 electrons each. That's going to be 10 electrons. Oxygen brings 6 electrons each. Got 2 of those, so that's going to be 12 electrons. We need 22 electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. We don't have enough electrons if we do that. Everything's got its octet filled, but we haven't placed all of our valence electrons. We erase that.
That essentially adds
2, 4, 6, 8, 10, 12, 14, 16, 18, 22, right? That gets us to the right thing. Now, when we want to talk about resonance structures and oxygen having a minus, so if I erase these 2 electrons and I put them over here, giving oxygen a little negative and giving this nitrogen a little positive, 2, 4, 6, 8, 10, 12, 14, 16, 16, 18, 22. I've still got my 22 electrons, so why doesn't this happen? That gets into resonance structures and the idea of formal charge. Formal charge, and I should put quotes in formal. Formal charge is a way to talk about the electron distribution based off of periodic trends. And it kind of puts a little bit of mathematics to it to talk about what's most likely. So when we talk about our stable Lewis structures, it's going to be the thing with the lowest formal charge. But now I'm getting ahead of where we are. That's what we're doing in class today. Like first thing after the quiz, we're going to talk formal charge. Yeah.
Wait, when you say skeleton, do you mean just write out the element?
Yeah, so I skipped the skeleton because we're already kind of like on the path. But let's do it for...
You do it on like a really complex one?
Let's do it for SO4 2-. Okay. So first thing we're going to do is count our electrons. Sulfur brings... I need a periodic table. No. I think it's 6. Sulfur brings 6. Oxygen brings, this one I know, 6. And we've got 4 of those, so that's going to be 24 total. -2 brings 2 more. So I'm going to tool this up. This is 32 electrons. I'm then going to do, so that's my counting. Then I'm going to propose my skeletal structure. I'm going to put the thing that is less electronegative at the middle. I'm not going to put any oxygen-oxygen bonds because those are super reactive. Single bonds, yeah.
So, I know the single bond between oxygens reactive. If you do a double bond, does that still
Double bond would work, but if you have an oxygen double bonded to an oxygen, will it want to bond with
Well,
anything
no.
else? No. If we looked at all of the other rules for the trends in oxygen bonding, we'd say no, except for in the case of ozone. Right? When we see ozone or carbon monoxide, right? So the nice thing that happens, and I'm getting ahead of myself again, but you asked an interesting question. When we start looking at these weird situations where like, ooh, that is not one of the bonding trends I learned about oxygen. This is not one of the bonding trends I learned about oxygen. Think about this. Is carbon monoxide safe? Is ozone safe? Upper atmosphere, it's great, but if it's lower atmosphere and you inhale it,
Not great.
really bad. Turns out these weird structures we can start to see like really reactive, right? We can start to see danger in the Lewis structures. We can actually start to understand reactivity and why. Like you look at carbon monoxide and you're like, this is the actual Lewis structure for carbon monoxide. Carbon's not satisfied, oxygen isn't satisfied. This stuff, when it gets into organic systems, super reactive because this is not in a stable energetic state. Carbon monoxide is produced by incomplete combustion reactions, right? You have to have these really high energy situations to create this molecule that is really reactive, and it'll go around and react with whatever it bumps into. Carbon monoxide is not an issue if we stop driving cars, because then we're not producing it anymore. It's going to react out of the environment. But we drive cars. So we get catalytic converters to just react it away and just turn it into carbon dioxide. Has its own issues, but less dangerous than carbon monoxide. Back to the problem. So that's what I mean by skeletal structure, right? We propose, and we're like, nothing's happy. Let's just go ahead and toss in all 32 electrons. Let's just make all oxygens have 8. That's 8, 16, 24, 32. Right? Everything's got its octet. Everything's got its charges. This actually is not the best. And why this is not the best has to do with the idea of electronegativity and electron sharing, right? This picture would suggest that oxygen can pull electrons away because sulfur right now essentially is sharing all 4 electrons with the oxygens, and 2 more of its electrons, because it had 6 at the start. 2 more of its electrons got totally stolen by the oxygens, right? So this sulfur is going to have some like formal charge associated with that phenomenon. And these oxygens, only having 1 bond, each of these is going to have some formal charge associated with that, right? And when we start looking at that, we're going to say, look, these things, this electronegative difference is not large enough for this to happen. There's going to be a more stable version of this. So that gets into formal charge. And the short answer is that. Where this oxygen is going to have like a little... Now, normally what we do again is we can represent like this oxygen is going to have like a negative formal charge. This oxygen is going to have a negative formal charge. Typically, we say that the 2 minus is, outside there. Again, because electrons are not static things that sit in one spot. Like that 2 minus is going to be distributed over this entire thing. Also, why did I put the double bonds there and not here? Resonance structures, right? So, again, like, yeah, it doesn't matter. Or, that is to say, energetically, they're identical.
Yeah.
Right? And if they're energetically identical, it doesn't matter. We can do any of them. And it turns out all of those exist because these things are all dynamic and moving. But I don't want to draw all 6 resonance structure pictures of this. So I say this one plus all of its resonance structures. Close enough, right? We're doing like 20% of the work to get 70% of the answer. We're like, good enough. Today we'll learn how we do formal charge to show that this is the best one, and we'll talk about resonance structure, talk about the other orientations of this. But for the most part, for the quiz today, that's not going to come up. Well, let me get this question. Just make sure I know. Okay, but anything related to this?
Yeah.
Yeah, go for it.
So when you say it's the best, does that mean that it's like the most stable
Best.
or like the most representative of what you'll see in nature?
Yes, essentially, right? It's the most most energetically stable, and and again, cartoon picture. These electrons are distributed over the entire molecule. Um, it's not it's all of these bonds are going to be like an average of all the resonance structures, but it's going to have the best balance of electron attraction and repulsion between the sulfurs, oxygens, and electrons.
But the original drawing you had with all single bonds, like that still works. It's just not the most stable.
Right. Yeah. So that would be a higher energy resonance structure, right? With because like sulfur and oxygen have similar electronegativity, so the idea that the oxygens could take those electrons away from the sulfur, pretty unlikely. But energetically, like, could happen, but it would not be the most stable. It would not be like a ground state. It'd be like an excited. It'd be like a higher energy resonance structure. And again, we're getting ahead. I love getting ahead. I like getting ahead instead of behind. But I want to make sure I answer any other homework questions people have. Let me get your question.
I have a question on 13 for the ones that
Okay.
have like multiple atoms in the first element. Like, how does the naming work for that?
I'm going to leave this picture up so we can talk more about it later. So problem 13, can you read problem 13 for me?
Yeah, give the systematic name for the formulas, and the two that I have questions on are Na2HPO4 and Mn2O3.
Mn2O3 you should be able to do. Na2HPO4, sodium hydrogen phosphate.
Okay,
Isn't it di?
do you have to say disodium?
No.
Okay, because I looked that one up because I couldn't do it and it said it was just
So
disodium.
there's essentially 4 different ways to name this thing. Disodium hydrogen phosphate, sodium hydrogen phosphate, and dibasic phosphoric acid. Right? So, and again, we get into that kind of like complication of like, what's the most scientifically correct name? And when I look at this, and one of the fun things about science is like, you can argue, and it's like, oh, well, what do the rules say? So when I look at this and I say, look, between the sodium and this common polyatomic ion, we've got ionic bonding.
Okay.
When we have ionic bonding, we don't say di,
Okay.
right? We let the charge tell us, we let the charge of the common ions tell us how many there are.
Okay.
So I would look at this and I'd say, the fact that I've got hydrogen phosphate here, or the dibasic phosphoric acid, that is going to tell me this common polyatomic ion is going to have a -2 charge, and that -2 charge will tell me that there's 2 sodiums.
Okay.
So
Okay.
I would go with sodium hydrogen phosphate.
Okay.
But depending on where you look it up, they call it disodium versus monosodium. So the reason that we have to specify is because there's a difference between NaHPO4 and NaH2PO4. And I would call this sodium dihydrogen phosphate. Notice for the covalent compound, I have to put the di in to say how many hydrogens there are. But the number of sodiums, the ionic bond, we can figure out from the charge.
Okay.
Okay, can you...
So then the Mn2O3, one more. What would you call this? It's not
Well,
magnesium.
it's oxide. O3 is oxide.
It's manganese.
Is it 3?
So is it like that?
Manganese 3
Okay.
oxide. Notice I don't need to say dimanganese trioxide, right? Because the charge for this ionic bond tells me the numbers. Essentially what you want to think about, if you remember back to when I was telling you my pet peeve for graphs, it's like, if your title is absorbance versus concentration, I'm like, rah, because you have redundant, useless information. If we say dimanganese trioxide, the di and the tri in that case are not giving us any extra information, right? It's redundant information. So we want to get rid of the redundant information, keep things as concise as possible.
Okay.
Okay. Other questions? Yeah.
Can you draw the Lewis structure for? It's really long.
Yeah.
Okay.
I can try.
HOOCCH2 CHCH2.
That?
Yeah.
So notice, I could have just said C4 H6O2. Same thing, right? This is trying to be a particular suggestive molecular formula. So C4H6O2, bunch of different possible isomers. HOOCCH2CHCH2, trying to suggest something particular. Remember, COOH suggests what functional group? Carboxylic acid. So I'm going to have a C, double bond O, single bond OH. Then I'm going to be attached to another carbon that's going to have two hydrogens attached to it. So there's my COOH, there's my CH2, and I'm going to be attached to a carbon with a hydrogen, and then a carbon with two hydrogens. And I look at this and I'm like, ooh, something's got to be different here because this carbon doesn't have 4 bonds, this carbon doesn't have 4 bonds. Double bond there. Notice the trends we learned from the molecular structures activity on Wednesday makes it so I don't have to do my 4 steps of count. Because imagine if I was like, okay, count all of the electrons in C4H6O2. Propose a skeleton structure for C4H6O2. Make sure everything's got it. It's like, yeah, we could do that. But because carbon, oxygen, hydrogen, and nitrogen behave very well and very predictably, we can just jump to these bonding trends that we learned and be like, we can just look at this and be like, 4, 4, 4, 4, 2, 2, all good. Same goes for all the hydrogens. That should be a valid structure. Real quick, that's the power of the trends we learned from molecular structures activity.
Can you go over the suffix and prefixes with like hypo and per?
So looking at the
Number of oxygens, right?
oh yeah. So I will do it for some common polyatomic ions. We don't run into the hypo and the per very often. And this is a relatively frustrating thing. I just want to make sure the focus. And so every once in a while, the camera decides to mess up its focus. So ClO3 minus is one of our common polyatomic ions called chlorate. ClO2 minus, chloride. And normally we just have to deal with 8 and I. Now, this gets into that kind of historical issue of they didn't know what these things were. They just knew that one seemed like it had more oxygens, one seemed like it had less oxygen associated with it. So they just named them based on the number, the ATE ending and the ITE ending, especially when you start learning your polyatomic ions, does not correspond to the number of oxygens. It corresponds to, more or less.
Okay.
Right? And so that's really frustrating because sulfate is
4.
SO4 2 minus sulfate. Sulfite. SO3 2 minus. Right? More oxygens, less oxygens. Not the specific number. 8 does not mean 3 oxygens. 8 does not mean 4 oxygens. It just means more or less relative to the compounds they're talking about, which is pretty frustrating. And most of the time, 8 and I is going to be good enough. And you'll notice most of those things are going to be 3 oxygens or 4 oxygens. Nitrates are 3 oxygen, chlorates are 3 oxygens. Trying to remember the other ones right now. I can't remember what else was on there. Sulfates of 4 oxygens, phosphates of 4 oxygen. So pretty common, yeah.
So number 13 COO would be cobalt 2 oxide.
CO. Oh yeah, that's cobalt 2 oxide. One problem is it turns out that you don't just have more and less. You can also have a lot more. Oh, not 2 minus. Sorry, that's just ClO4 minus.
That's where you add the per. Okay.
And you can have a lot less oxygens.
Okay, that makes sense.
And that's where you add the hypo. Right, so you kind of have this extra adding on because they're like, oops, there's more compounds. What do we do? And it's like, well, we already used 8 and 9. Let's just toss on another thing. Sometimes I wish that we could restart all of the naming conventions from like everything we know now. Like rename all of the common polyatomic ions, rename all of the compounds with like actually understanding molecular structures. I feel like there'd be a lot better way. Someday when we make contact with an extraterrestrial population, they're going to be like, oh dude, you should totally change the way you name these. We do it this way. And we're going to be like, why didn't we do it that way? It's so much better.
What are the functional groups we need to know at the moment?
Functional groups you need to know
I think you
are
had them on the board earlier, but that was right when I came.
alcohol. Did I spell alcohol right?
Yeah.
Yeah.
That word looks so weird to me every time.
There's a Jamie Foxx song called Blame It.
Carboxylic acid.
Alcohol is just an O and then an H at the end.
Yes. And ketone. Those are the 4 you need to know now.
Okay.
By the end of the quarter, well, probably by the end of next week, we'll do all of the others. We can toss another one on there.
I mean,
It's not yet.
what can you draw the aldehyde and ketone?
Yeah, so I'll do it with what carbon chain do you want? How long do you want your carbon chain to be?
Butane.
3
So do you want butane or propane?
Oh. That's butane.
Let's say butane. Butane would be 4. Monkeys eat plenty of
Oh,
bananas.
right, I forgot.
So we can do 4 carbons. So we can do 1, 2, 3, 4. We're gonna have a bunch of hydrogens. Oh wait, I can't do that yet. I'm getting too far ahead of myself. So I know I also want more space. So we're gonna do aldehyde and ketone. Do carbon, 2, 3, 4. If I put the double bond here, what's it called? Double bond oxygens in the middle. Which letter's in the middle of the alphabet, A or K? Okay, so
Ketone.
it's a ketone. If we wanted to name this, this would be butanone. And technically, this would be butane 2-one. It's not butane, it's not buta-2-1, it's butane-2-one.
Okay.
Because that's the ketone. I would call it, and because I learned these naming conventions a little bit early in life, I'd call it 2-butanone.
I have one question on the.
Well, let me do the
Okay.
ketone as well. So if we switch it to the end, and notice the end here and the end there would actually be the same thing, right? It's just symmetric. That would be, what's at the beginning of it? Aldehyde.
Oh, so it's just whether it's in the middle or the end.
That would be butanol.
Okay.
Yeah. And then if we switched it to an OH group, butanol, if we switch it to an alcohol. And then depending on whether it's 1 butanol or it's 2. Oh, sorry, that's an OH. And then I'd switch that to 2 butanol. The number out front just tells me which carbon in the chain I'm attached to. Until we get to diols, which is double alcohols. But we'll do that in the IMS lab.
One more question.
Yeah.
So for 19, it says the element you have to draw is C4H8O, and then it says include carbon ring. So what I do, I just like put like 4 carbons around each other and just like single bond them. Is that
Yeah.
fine?
Okay,
Is that kind of carbon ring?
Carbon rings are 6.
C4H8O.
Yeah.
Carbon rings are 6, 5. You can do 4s. Sometimes there's 3s. 3s are like epoxies. You can do 8s. There's a bunch of different things you can do. You can do 60s. That's a buckyball. It's not really a. But So doing carbon, 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 like a ring like that. Jonathan, is that what you did?
Yeah.
So yeah, you probably made, and then we do 1, 2, 3, 4, 5, 6, 7, 8 with an OH there, hydrogens everywhere. Yeah, this is a fine Lewis structure. The cyclic butanes are not very stable because this bond angle, we're going to learn about bond angles today as well. Those bond angles are pretty strained. It's a valid Lewis structure. You would get credit for drawing it. I think what would make it a little bit, and then there's always like, what was I expecting? If you do,
Oh, so you can't put the oxygen.
yeah, you can put the oxygen in the ring. Those are all hydrogens.
Yeah, I thought that would purely be like that's it, literal carbon ring, like nothing.
No,
else.
yeah, this counts as a carbon ring as well.
For sure. Right on.
Question about this or something else?
Go for it.
I'm asking a question.
Okay. Number 6. It was like about the unit cells. And I
Okay.
don't really understand what, like, it's asking for when it says what is the change in the unit cell.
So, okay, so I can't draw this one. I'm sorry. You're gonna have to look at the homework if you're watching this video. Pull up homework 4 from Chem 124. Look at problem 6. Look at those 2 pictures. It's just asking you to talk about the actual physical observable changes between them. So, for example, the structure of, like, I think it's the oxygen is still in an FCC, but the gray atoms change from being like a simple cubic to being like this weird, like, twisted thing, right? You know, so the space between the atoms changes as well. The size of the ions, the atoms changes as well, right? There's these very visible odd changes that they're trying to represent in that picture.
Okay. And I'm still a little bit confused about how to determine the coordination number from just looking at the unit cell, like looking at the picture.
So you have to be able to pick an atom and then three-dimensionally imagine all of the atoms that are closest to it, so anything that would be touching it.
Okay.
In some of the pictures though, like
some of the pictures
they're
is
not none of them
really
are
hard
touching
to.
any of them.
Right. So particularly in these pictures, they are doing, again, and it's three-dimensional representation versus actual representation, right? So we can represent, you know, this unit cell, just putting dots, right? So this would be like a FCC. I'm not going to draw it all out. In reality, if you did the space-filling model where you were taking up as much space as it should.
Isn't that a BCC?
No, because that one's on the face, right? And this one's on the face. Right? If you were actually taking up the space, you wouldn't be able to see inside of it at all. Right?
Okay.
So in order to make it so you can see inside, they shrink these down to make it so there's space where you can see through. But in your mind, you have to be like, okay, but these things are going to fill up all of the space.
Okay.
Right?
So what would the coordination number be for that one?
So for this one, if it's a face-centered cubic, I say, okay, this one on the face is going to have 1, 2, 3, 4 nearest neighbors.
Okay.
However, it's also going to have
Is there one inside that it would be?
no, it's face-centered. So now I have to think about this.
They're just touching 8.
Yeah, because it's also going to be, because now I have to like imagine it growing out in three-dimensional space and think about those other atoms it could be touching, right? And that's where I start to like have to think a bit, and especially because I drew a not very great picture. It's got these 4. It's also going to be, I'm trying to think about the ones on the faces. I think it's going to be 8.
I got 8.
Face center cubic's 8. Simple cubic is 6. Face center cubic is.
Face center cubic was 12, and then body center cubic was 12.
Yeah,
You're right.
it
Yeah,
is.
face center cubic's going to be 12. So, oh right, because I've also got this one, and then on this face I've got one, on this face I've got one. So it's 1, 2, 3, 4, 5, 6, 7, 8, and then I've got that extra layer up here that's 9, 10, 11, 12.
Okay.
Yeah, this is where my drawing on the board for three-dimensional representations is like, sorry, doesn't work there. But if we did the Z diagram, it'd be a little bit more visible, right? Because you'd have, right? And then our next layer up would be this. And we'd be like, okay, so it's got these 4 next to it, and it's got these 4 next to it, and then it's got another layer down that's another 4 next to it.
Okay.
So then it becomes, and that's part of the wonderful thing about Z diagrams.
Got it.
That's it for officers. I can do like 1 or 2 more quick questions. Yeah.
Can you just do number 7 for like where
Yes. I said.
yeah.
What's number 7?
Parts can you-
Yeah, so 7, the problem with number 7 is we have to use an approximation in
Right.
order to do it. And essentially what you have to do is you have to imagine from this corner up to the back corner, right? So going all the way across the diagonal of the cube, you have to imagine that you've got your oxygen, then you've got a zinc, then you've got a gap, then you've got your oxygen, then you've got your zinc, and you have to like, the approximation that I found that most people use online is essentially you have to kind of think what's that gap going to be, because technically, and I was racking my brain trying to do all of the trigonometry to do this the correct way, to do it like actually correct. But everything I was getting was like, ooh, I'm gonna have to use an approximation somewhere to like say this angle's 60 degrees or this angle's 45 degrees so I can do the rest of it. And it turns out that it's a reasonable approximation to just say that this is an oxygen atom as well. So we've got oxygen, zinc, oxygen, zinc, oxygen. So I end up, if I count my radii, I end up with 4 radius of oxygen plus 4 radius of zinc. Right? And that's going to give me my long diagonal. It turns out that if you look at a BCC, again, looking across, oh, that's what I did wrong. Looking across a BCC, you end up with 4 radius of whatever it is you're looking at. So you can say that this is approximately BCC with 4 radius oxygen plus radius zinc, and then just use your equation 4r over root 3, right? So this is your radius. It's an approximation. It gets to the right idea. I did it quicker than I would have liked because the office hours is over. But this is a fine approximation. I'm not entirely thrilled with it, but anything else I found that worked was trigonometrically challenging. Like saying the word trigonometrically.
Just real quick.
Yeah.
Doesn't that sulfur have 2 new bonds? The in green.
Yeah.
Is that not a problem?
Nope.
But like 8
But like,
octet. Okay.
so remember the octet. No, it's the octet guideline, right? So what are the things that follow the octet guideline?
Carbon.
NO.
Carbon, nitrogen, and oxygen are pretty much the only things that do it, except nitrogen breaks it sometimes. Right? So this, and then remember, where the octet rule comes from is this energetic argument of getting your valence shell full. Sulfur also, because it's in the 3rd row, can also use those d orbitals. And so instead of the rule of 8, you get the rule of 18. Right? So it turns out anything past that 1st row, which is oxygen, you can start getting a lot more bonds.
So in theory, you can have 9 bonds. That's first.
In theory, but then you have to go to the actual energetics of what's going to be possible. Right? You got to be careful what we do on paper versus what actually happens. Okay.
I have.
That's it for now. I'm just going to stop this now. Hope you enjoy.